by phases, by components, by degrees of freedom. What is the relation between all these terms and how they plays an important role in the study of chemical system? Whether it's a homogeneous system or a heterogeneous system, they will play an important role for us. So till now we have studied water system as well as sulfur system. Now let's begin with another one, which is a two-component system. Two-component systems are also referred as eutectic systems. Why is it so? And which are the examples of it? Let's go into detail for it. Here, when a single phase is present in a two-component system, the degrees of freedom is 3. So we can write capital F is equal to 2 minus 1 plus 2 is equal to 3. Right? Thus, when a two-component system consists of a solid and liquid phases only, and the effect of pressure may be disregarded, then it is necessary to take into account by remaining variables like temperature and concentration into account. And when we take temperature and concentration into account, such kind of system is known as eutectic system, in which only solid and liquid part is present, while the gaseous part will be absent. So such a solid liquid system with a gas phase absent is known as condensed system or eutectic system. For such kind of condensed system or eutectic system, we can write that in any kind of eutectic system, the phase diagram is temperature composition instead of temperature versus pressure diagram, right? So two metal alloys are its examples. Here we can study with the use of eutectic system that how the formation of simple eutectic point occurs, how a substitutional soil solution forms, along with it a compound formation with incongruent melting point can be possible, and even the formation of partially miscible solid and interstitial solid solution formation can also be understood with the help of any kind of eutectic system. So it will give us an idea about many metallurgical operations as well as their uses in different kinds of industries, right? Now let's move on to the next one. The first system that we will take a look here is a silver lead system, which is also known as AGPB system. This system is widely asked in GTU, as it's a very important theory. Even this alloy is widely used in industries also. So the system has two different components. Number one, silver. Number two, lead. The boiling points of silver and lead being considerably high, the vapor phase is practically absent for such kind of condensed system. Thus, AGPB is a condensed system with two phase, or I should say it's a three-phase system, right? We need to consider only the two remaining variables, namely temperature T and concentration C. Now, let's see the phase diagram of AGPB system. Here we have temperature on first axis on one axis while concentration on the another axis. The composition will be taken in percentage form while the temperature will be taken in degree Celsius form. As you can see here in the image, we have different curves as well as different points, that is a eutectic point, as well as we have here the areas present, right? So if you can observe the composition at the starting of the curve, we have 100% Ag and 0% Pb, while when we reach at the temperature 303 degrees Celsius, 97.5% Pb is present, while 2.5% Ag is present. As you move forward, it becomes 100% Pb and 0% Ag, right? Now, the two different points, 961 and 327, are the melting points. First one is the melting point of our silver, while another one is the melting point of our lead. So at that point, when they both combines, the composition and the temperature that becomes specifically at a particular eutectic point, they mixes with each other. So we get such kind of graph, and after that we get such kind of alloy. Let's see the salient features of the diagram. Here you can observe two curves AC and BC. So for that, f dash is equal to c minus p plus 1. This is a Gibbs phase rule for any eutectic system or condensed system. Let's put the values here. We get 2 minus 2 plus 1. That becomes 1. So f dash is 1 for our curves. After that, eutectic point C, which occurs at 303 degrees Celsius, f dash is equal to c minus p plus 1. At that particular point, 2 minus 3 plus 1. So f dash becomes 0. Remember that at triple point and eutectic point, f becomes always 0. Whether it's a triple point, whether it's a eutectic point, it becomes 0. Now, three different areas are present. First one above ACB, second one below AC, third one below BC. Right? So for that, we have different things. Like as you can see, we have below AC, so we get solid AG oblique solution. We get the solution of PBAG as well along with it. After that, it converts itself into liquid, right? So here we get f dash is equal to c minus p plus 1. So 2 minus 1 plus 1 is equal to 2. So the value of f dash becomes 2 here, right? Now let's move on to the another system. Which is this system? It is zinc-cadmium system. Zinc-cadmium system has almost the same features as that of the silver-lead system. Here, just only the composition and the temperature varies as the metals are varied. So to form any kind of alloy of zinc and cadmium, we have to understand the phase diagram or the behavior of such kind of metals when they mix together. Here, as in the image, you can see that at 270 degrees Celsius, when the composition is 83% of cadmium, while 17% of zinc is there, at that particular point Z, the eutectic point occurs, and there both the metals starts to combine with each other. At that moment, after that moment, they will combine with each other. Here the points 419 degree is the melting point of zinc, while 321 degree is the melting point of cadmium. Now, let's observe the salient features of the particular diagram. Here two curves are there. One is xz, another one is yz. Let's calculate f dash for it. We have f dash is equal to c minus p plus 1. Let's put all the values here. That is 2 minus 2 plus 1 becomes 1. So it's a monovariant system. Now, for eutectic point Z, we get f dash is equal to c minus p plus 1. So here 2 minus 3 plus 1 becomes 0. As three different phases are in equilibrium with each other, while two different components are present at that particular point. Now, next is three different areas. First area is above xzy. Second area is below xz. Third area is below yz. So we have to consider that as number of components 2, number of phases 1. Let's put the values in condensed phase rule. F dash is equal to c minus p plus 1 becomes 2 minus 1 plus 1 is equal to 2. This is how we can calculate the variant or the particular kind of degrees of freedom for our system. Let's move on to the next one. Next system is the ferric chloride and water system. A very important, a very critical system. This provides an example of a 2-component and 7-phase condensed system. 2 different components are present and 7 different phases are present here. How it's possible? Let's observe it. Here, as in the image, you can see the phase diagram of this system. One side shows temperature, another side shows composition. Now what will happen here? As you can see in the image, at 0 degree Celsius, we have 100% water. So that is the freezing point of water. If you lower the temperature, ice formation will be there in this particular area. After the point B, as you move from A to B, now the formation of Fe2Cl6 came into existence. So, till point C, the formation of Fe2Cl6 into 12H2O starts. At this particular point, this formation occurs, and at a particular temperature, it starts the formation of Fe2Cl6 into 12H2O. At particular point D, it will degrade itself and starts converting itself into Fe2Cl6 into 7H2O. So from that point till E, the formation of Fe2Cl6 into 7H2O occurs. At point F, it is totally converted into another one, which is Fe2Cl6 into 5H2O. Now, after this formation of this happens at point G, H is the point where it stops formation of 5H2O or Fe2Cl6 into 5H2O. After that, it converts itself into Fe2Cl6 into 4H2O at point I. Now, what will happen? At point J, all the water molecules disappeared and Fe2Cl6 solution starts forming. So, at point K, Fe2Cl6 totally gets converted into solution, and after that 0% H2O will be there and 100% Fe2Cl6 solution will be formed. So in this manner we will have a 2-component while 7-phase system, right? Now let's see the curves. We have AB, BCD, DEF, FGH, HIJ and JK. For that we have F dash is equal to C minus P plus 1, which is 1. So it's a monovariant system, right? Along with it, what we will have here is a congruent melting points. That congruent melting points has F dash is equal to 0, which is C, E, G and I. Now, next is eutectic points. Which are the eutectic points present? So D, F, H and J are considered as eutectic points. So F dash for it becomes 0, where 3 different phases and 2 components are in equilibrium with each other. So in this manner, we can understand that how Fe2Cl6, or I should say ferric chloride and water system, can be understood. Next, we will see in our next lecture. Thank you so much everyone.